we can thank Dr. Zhang again, and we can move on to the next session. And of course, if you have any more questions to Dr. Zhang, please feel free to leave your questions on the chatting board. In the meantime, we'll go to the next speaker. So our next speaker is Rudy Raymond from IBM Quantum. So Rudy, you're connecting from Tokyo, right?
Yes. Yeah. I'm in Tokyo.
Yeah.
So I think we met in Korea, but in Daejeon. But
yeah. So maybe could you try to share your slide?
Sure. Can you see my slide?
It's coming. Yeah, so we can see it fine. At least I can see it fine.
Okay.
Yeah, so I'll just pass it on to Rudy now.
Yes. Okay. Thank you very much, Daniel. Thank you very much, Professor Kevin. And yeah, it's a pleasure again to be able to present our work at the workshop. I think last year I also gave a talk, and actually it was some of this work actually was inspired when we met. So Yano-san, the co-author of this result, actually also attended this Q2ML in Korea last year, and we had a discussion, and then we worked together. So it was really, I think it's sad that we cannot meet offline, and I think this. Online is good, but sometimes meeting people at a conference, workshop, even if we work together in Japan, it's really interesting. So I hope maybe next year will be different. Yeah, so my talk will be about efficient discrete feature encoding with quantum bits. So this joint work with my college at Keio University, and some of them have been presented at IEEE Quantum Week 2 months ago, and the paper is on the archive. So the outline of the presentation is, first I will introduce this classification with quantum enhanced feature space, but maybe this will be brief, because Daniel, I attended his talk in the morning, and he already touched some of this also. And secondly, I will talk about quantum random access coding, which actually we have been studying this for quite a while. And we found that these primitives of quantum information can be used to encode binary features in variational quantum classifier. And that based on a series of our work in 2006 and 2007. And what is interesting about this random access coding is we can use n qubits and quantum bits to encode up to 4 to the power of n minus 1 there, classical bit, so that we can extract any one of these information bits. So what we call that Holeful bounds forbid us to encode more bits into quantum bits, but if we allow errors, we can actually put more bits. So that's what we use actually. And the third one is experimental result that we demonstrate on real device and also on simulators on using these primitives of random access coding. So of course, this is very trivial that in many tasks in machine learning, and that include many important problems, for example, real value prediction, stock market, climate, temperature, maybe coronavirus spread, something like that. And also classification, right? So we have binary classification, multi-class classification, and also pattern discovery, because we know that some recent results saying that quantum device can generate some patterns, while classical device to generate needs supercomputers. Then this means that probably this generative method can be used to identify or classify pattern that they can generate efficiently. And in Tokyo, we also do this pattern discovery, but more on the approach of brain-inspired network, which I was also involved in this until I joined IBM Quantum. So It's also open source, and you can see on this site. And I think like the main motivation of using quantum computing for machine learning, of course, we have speed up. But I think like if you tell persons working on this, maybe like it seems that quantum bits can encode more information, right? Even Hohlefeld forbid it, but superposition seems to be able to provide some encoding, and that actually what will be the main point. And for this, let's look at the formalization of machine learning for binary classification. So we are given input, which is training set and test data sets, and like here with the label y. So X is kind of features of this data that you want to classify. Y is the label. Let's see the simplest task is binary classification. So the label is will be 1 or -1. And objective is, of course, to be able to classify them. And this can be expressed by finding a function f of x, so taking the feature vectors and compute the label. And then with the prediction labels or with the labels that their multiplication always bigger than 0, which means they agree on the labels. So how to find this function, right? So this is really like the subject of support vector machine. So this slides, this figure are taken from the MIT online lecture. And this is like really a very old problem. Like if you can find this classifier, which means that you can arrange the data points as a point here, for example, the red points, and another set of data as a green point here. And then you can find a plane, hyperplane here as shown as a line that separates this green or red points from the green points, right? And the support vector is like trying to find this plane that separate them the most. So the distance here is the largest. And this the formula to compute it. And so it's really like linear function that if we can find this kind of arrangement on some higher dimensions, that means like we can find a linear classifier so that given the feature vectors, you just weight it linearly and by some shifting by some b, then you can determine the sign of this label or either 1 or -1. And the hyperplane is actually all points that satisfy the weight W, the inner product with X plus B is equal to 0. And all of this X that satisfy that determine the hyperplanes that you want to compute. And which is interestingly because we in 2007, we saw that if there is such a arrangement of in, let's say, in a dimension k that for this linear binary classified dimensions, then we can map all these data points on this dimensions into quantum states and the hyperplane here into POVM, or positive operator value measurements. And all of these measurements, POVMs, and this data quantum state only use half plus log k plus 1 qubits, which is exactly, there is no big O order there. So this half log k plus 1 is actually like, if you try to do it classically, you need log k bits. Or so that means like here we have advantage, of course, very small advantage, half advantage of these things. But nicely, like we derive that if we consider like what quantum communication complexity problems, we find like exactly half separation between quantum and classical, at the result that we have. And also like we work with some college to solve some query complexity problem based on this arrangement argument of hyperplanes. So, well, this is very detailed, but I think I will just skip it. But the idea is like, if you write this quantum state as density matrix, we have free variables. The number of free variables is like for, let's say for 2 qubit, the number of variables is like 15. And then for n qubit of, here is pure state, but for generally for mixed state, there are more free variables. Then when you can write it as a density matrix, you can identify the free variables, and then we encode all the information on these variables. And for measurements that also like more complicated way. So you can see this on the paper that on the archive about more than 10 years ago. So then what are things like we can map measurements also to the hyperplanes. We can map the feature vectors to quantum states, and good things like this probability of seeing 0 or 1, of observing 0 or 1 that corresponds to either the levels are 1 or -1 that I saw before, is actually nicely one-to-one correspondence. So and that means that we can map this arrangement of points and hyperplanes in machine learning or binary classifier into a system of quantum measurements and quantum states. And the success probability, of course, can be very small, but here we don't care at the moment. So it's like quantum weak learner, so we can allow it to be only success with small probability. And yeah, there's some detail here that I will not explain. So, but getting back to this binary classifier, so it's really like what we want is to find a binary classification function of f of x, taking x and finding the weight w, and then with some shifting, and then compute the levels, which is just the sign. And this can be formulated as a hard support vector machine formulation, hard SVM, while we are not allowed to label it wrongly, so it's always correct with these constraints, or soft SVM, which like we are allowed some error here, epsilon. So our prediction function here, w times x plus b, can be like can have an error epsilon, but this epsilon will be penalized so that the objective function is minimized here. So the idea is like, of course, if our data given as x here is already separable for the arrangement that we showed before, then well, we can just try to find this w and find this by some equation. But of course, there are cases where the dimension is too low, then we cannot find this. Then we have to embed these features into larger ones. So here from d dimension to n dimension, where n is bigger than d, then let's consider this mapping as phi of x. Then here on the higher dimension, they're still linear, but of course on the lower dimension might not be linear anymore. And then of course, then we can just apply the previous method to find this linear things. Now, how can we use quantum computing for this nonlinear embedding of data sets? This is like a slide that already been used many times. So like classical bit, it's actually, if you think of classical bits, either 0 and 1, and they're probabilistic. So you can write any linear combination of 0 and 1 as probability portions, then they're actually aligned. While a quantum bit, well, we are familiar with Bloch sphere, and they're actually all pure state can be written as a point on the sphere of a unit ball. But if you think about mixed states with probability mixture of quantum states on one qubit, they're a ball here. So it's 3D dimension, right? Now, of course, like this is like what people will say about this. We have this, if we have n qubit, then we can we have this exponential growth like this one. But of course, this is not true for if we consider the Holevo bound. But okay, the idea is like if we have feature vectors, and really like quantum computing is really about matrix and vector, then we can map this d dimension of feature vectors to n qubit quantum state, so that the element of feature vector become the coefficients of this probability amplitude of our quantum state, which is like amplitude encoding that Daniel has talked in the morning. So this is like how we can encode this as an amplitude encoding. And yeah, so in idea, it's like actually if we use here is a 2 to the power of n, but if we use a mixed state, we can encode up to 4 to the power of n minus 1 elements of this feature vector, real value feature vectors. And of course, like all this mapping, right? So we have x, and we have to find this phi of x, and we map it, and we also have to find a w, and how to compute this w times phi of x by quantum states. So the idea is like we can find a mapping by some unitary transformations that takes all quantum state from 0 to the quantum state, the mapping to quantum state on higher dimensions on a Hilbert space. And then the inner product of them can be computed by this quantum circuit that create this phi of x and also the inverse of creating phi of y. And then we can compute this inner product between the mapping of y with the mapping of x, and then measure all 0, probability of all 0 outputs here. Then it's actually this quantum kernel estimation on the paper that our college has presented. And yes, for the variational quantum classifier, what we do is like mapping this to quantum state, mapping the data points phi of x to quantum state of ket phi of x, hyperplane w to measurements. So the measurements like projecting to some pure state here w zeta. So zeta will be fixed for all x feature vectors, and for linearly separable things, then it's actually like we just evaluate the inner products between this measurement basis and the quantum state that we have, and then find this arrangement. So it's really like variational quantum classifier is about arrangement. And of course, we can do this with a variational quantum classifier, as we saw in this picture. So departing from all 0 quantum state, we map our data of x. So this unitary is depend on x. And then after that, we try to separate it with this w. And this, so there are some variation, like hybrid method or variational method of doing this on the training phase and the classification phase. And the idea is like why it might have quantum advantage, because all of this encoding of our data into quantum state might be hard to do with the classical computation. So we can do it efficiently only by using Hadamard gates and also diagonal gates like Z or control Z or Z gates, something like that. But they're already shown that it can encode sub-P hard problems for one diagonal, and 2 diagonals are conjectured to be hard to approximate. So there are some weird consequences if classical can do this in complexity theory. So this is like example of a variational quantum classifier. And like there are many ways to encode the real value feature vector, like squeezing, amplitude encoding, and density operator encoding, and many others. But here, what we found that all of these talks mostly considering the mapping real valued F element. But if you work on real world data set, you'll find that many of these features are really binary or categorical features that thinks about a gender, right? So male or female, or maybe like age group or something like that. So they're mostly categorical or even binary. So in this case, like what we propose is a quantum random access coding. So the sender can encode n bits of information into less number of qubits, m here, m qubits. But the idea is like the receiver can extract only one of them, but not all, so only one. And this probability is like bigger than random guessing, bigger than half. And there's no prior communication or entanglement are allowed. And this actually has many applications in locally private information retrieval, random numbers, and many others. So the idea is like if you can do this, you can imagine if there is a satellite very far away from Earth, it can just send one qubit or like one qubit that contains all telephone number of all person in the world, for example. And then each one can choose his which of his phone number by the same from the same qubit. Of course, there are some limitation of this. So what we have shown that actually like you can encode 2 bits into 1 qubit and 3 bits into 1 qubit. with this success probability, but somehow you cannot encode 4 bits into 1 qubit. So 4 is the limit, 3 is the limit, and the success probability is also optimal. And we can generalize it for any number of qubits here for the impossibility results. And we also recently saw that some possibility result, like for 2 qubits, like what is the success probability and what is the best way to encode your bit strings. And remember that this is encoding the bit string. So, and the construction of this randomness coding is really geometrically is very beautiful. Like there's 1 qubit gate is block sphere. And like, for example, encoding 3 bits of information, what you need to do is like really putting this hyper cube that has 8 corner here into this block sphere. And you can see like all 0 here, 0, 0, 1, 0, 1, 1. And the measurement of observing the first bit, second bit, and third bit is only progression on along the XY, YZ, or XZ bit, plane here. And then you can see that this success probability. And there are many results also on like 2 qubit randomness coding, and we improve it a little bit. But the idea is like, it's very simple that instead of, at the current moment, like if you have binary variables in variational quantum classifier, and also like real valued feature vectors, we just assume this binary feature vector as a real value, right? But here, what we propose that if you have really binary or bit strings, why not use this random access coding? Because then it can reduce the number of qubits that you need. For example, here, you need n qubit for n-dimensional feature, but for our method, you can reduce the number of qubits. So, and surprisingly, like this is like really what we found on working on like real data, let's say breast cancer data set here, and you see that all the features are categorical. So there is even no real valued feature. And then we choose this 4 feature here, like number 3, 4, 6, 7. And this is the number of categories there, and this is the number of bits if you encode it with classical bit strings. And we run traditional VQCs that need 4 qubits because there are 4 features there. But when we use our random access coding, we only need 3 qubits. And the number of variational parameters is 30 instead of 40. So we also reduce the number of parameters. And surprisingly, we got lower training loss. So the orange one is our method, VQC plus QRAC, with 3 qubits and 30 parameters. And our training loss are lower. And also our training accuracy and testing accuracy are also higher than traditional VQC, as you see here. And this is like what happened if we have all categorical binary features and just replacing it with random coding, reducing the number of qubits and improving the accuracies. And we can also have similar observation on mixture of categorical and real valued features. So of course, this is really what happened in real world data. So all the data can have categorical, integer, real numbers, and like that. And we saw that we can reduce like 3 qubits into 2 qubits. The number of parameters also becoming less. And surprisingly, the accuracy also increases instead of the same or decreasing accuracy. So you see here like 0.85 accuracies for this heart disease problem. And I think what I also find surprisingly, by reducing the number of qubits, we found that even we got some better simulation result on quantum device than the simulator. So it seems that the simulator, because it's using pseudo-random number, it can get stuck at some local optima. But if we run it on our quantum device, it can escape from local optima and then get a better classification result than this simulator. And also for training loss, we can get better. Of course, this is really about random number, I think. And we ran this on 10-day experiment. So it's a long time experiment and also some other device and observe the same tendency. Yeah, so in brief, like what we have shown that we've saw how to use this random access coding. And of course, that this is really nothing that like if we have 20 qubit device, we can encode quite a long binary features. Of course, this encoding will require a C-node gate and many other gates, so it might not be easy to do this. But this really direct and simple application of quantum information primitives. And of course, there are limitations of randomized coding. For example, like if the out label of our data, orange one and blue one, like this one, there's no plane that can separate different color points, also for the 3-1 random access coding. But there are very easy way to mitigate that. For example, like we can use latent qubit proposed by Lloyd and al. Just add 0 qubit there and let the classifier learns how to use it. And we can also use copying, so use the same random access coding twice, or you can use higher dimension of random access coding. And we can see that all this training loss improve. So using higher qubit of random access coding is better than copy of random access coding in latent qubit. Also recently, I worked with my student at University of Tokyo of extending this variational quantum random access coding with the metric embedding that also proposed by Lloyd et al. At the beginning of this year. So we've seen before, like if we fix the embedding of binary features into a cube here, there are cases that we cannot separate this red one from the blue one, but we can avoid it by using quantum embedding idea of Lloyd. But here, the quantum states are not spread well, but we've introduced the regularizers that make them looks like quantum coding, then we can get better classification result. And actually, like that, what we tried on 3-qubit device on solving this Titanic survival data set. We also extended this quantum neural network model of Farhi and Neven to solve the MNIST handwritten image with 9-qubit device. And the classification accuracy is like 0.91, which is quite nice. So, and with less number of qubits. Yeah, so this is like just to conclude my presentation, that we have introduced this randomized coding for binary feature, discrete feature, which I think very important for machine learning. And we also have many experimental results, including like credit card transaction data set, which also include many discrete features. And so that's just to end my presentation. It's about time. Thank you very much.
Thank you very much. So do we have any questions? I mean, feel free to speak on the microphone, or you can also leave your questions on the chatting board. And there is one question on the chatting board asking whether the slides will be available later. I think we need to like work a little bit on this just to, so we'll have to like work on this to be sure that we. So as an organizer of this event, we'll work on it. So we'll have to like remove some confidential slides and so on, so that we can make it available to public. But we'll work on it after this event, and we'll let you know. So I have just one question about your presentation, Rudy. So, I mean, I really like the idea. I mean, I've also very briefly mentioned this like quantum feature map, and I really like the idea. But do you know, can we also, but it seems that, when we do quantum feature mapping, we can only, I mean, we can encode like high dimensional data, but it seems that we can only encode like one data per circuit.
One data per circuit?
So we could have like many data points, of which, and each data point could be like, could be mapped onto higher dimensional space. But when we like really, when we really implement it with a quantum circuit, it seems that we encode like one data per circuit.
Yeah. Yes, I agree. Like, so I think what you said that this encoding, right? Really, like for exactly, each X, you have to build it. Yeah, I think that's really true, right? So yes,
So
So
are you guys like, thinking about, like a different ways, like a different circuit designs and so on, such that it's also possible to encode like many numbers of data in one go?
So I think like that's I think Kevin work also, right? So like if you have this control like controlling something, probably we can have this universal, but
Yeah,
I
yeah.
think Kevin also work on this. But yeah, but I think that the limitation that we have because we cannot apply this control gate, something like that. But once we are clear from that, probably there's more better way instead of like generic ad hoc way to generate this. Maybe some generic way to do this. But at the moment, yes. So I have to admit that there's limitations. And really, like for example, computing the kernels can be very time consuming because that grows with the number of samples. So yeah. I do agree. So maybe we need. I'm not familiar with this, like how to mitigate it, but I think Kevin may be more knowledgeable. Yeah.
I mean,
Well, I'm on the same line, but just I have another question. So you tried some, the variational quantum circuit models, right? And
Yes.
what could you show me some example that was very, effective and efficient? For example, you just showed it as a black box, but I just want to have an idea what kind of the VQC could be
Yeah. So yeah. So this is
powerful.
yeah. So the idea is like we here like we, for example, if you have 3 bits of data x1, x2, x3 here. So instead of using 3 qubits, we use 1 qubit, for example.
Right.
Because we can encode these 3 bits into 1 qubit. So reducing the number of qubit here.
Okay, so that conversion was done classically or with
Yeah,
quantum
so
mechanics?
because this is like this randomness coding is really like there's a fixed encoding. So you know that if your state, like if your bit is 000, then you have to map it into this corner of block sphere, and this is a fixed unitary, right? And yeah, so this is like kind of like, do you have a dictionary on how to do this?
Okay, I see. Okay, all right. So that is basically done by the classical calculation.
Yes.
Okay, so you compress the data in the classical domain and create the quantum state that corresponds to the data.
Yes.
Right. Okay.
Which is what also Daniel mentioned, right? So this really like depends on the data. Then I change my circuits. Yes.
Right. Okay. That's good idea. Okay. Well, thank you very much.
Yeah, you're welcome. Thank you.
do we have any more questions from audience? I mean, if not for the time being, then please feel free to leave any comments, questions on the chatting board afterwards. But for now, let's thank Rudy again